Very good morning. Today is lecture 9 of the third unit, SQL queries, constraints, triggers, and schema refinement. We have completed SQL queries, constraints, and triggers. We are going to the schema refinement. In the schema refinement, uh, we have studied, we have gone through till this dependency, that is decompositions and anomalies. We have gone through all this. So active databases and what is active, what is passive. So all this and what are the anomalies, what are the queries we can do in this, what is decomposition, what are the properties of that, they are lost. Okay, now coming to this. Okay, now we have to start this. And before that, I want to give my introduction. This is Dr. Gausia Banu, teaching on Unit 3 on schema refinement extensions on database management system. Okay, let's come to decomposition. What is decomposition? Decomposition is nothing but breaking up into smaller subtrees or substructures for in the relation, so that we can avoid all types of anomalies, redundancy, and consistency. So decomposition of a relation can be completed in two ways. What are the two ways? Lossless joint decomposition and lossy joint decomposition. So lossless joint decomposition, consider there is a relation R which is decomposed into sub-relations R1, R2, and Rn. This decomposition is called lossless decomposition when the joint of the sub-relation results to the same relation R that is decomposed. For lossless joint decomposition, we always have R1. What is this symbol called? This is a natural join. To R2, natural join with R3, and so on, natural join to Rn, where all these sub-relations refer to the root relation, where this symbol is a natural join operator. Consider the relation where R is a set of ABC attributes. So this is there. We have gone through this one yesterday, but for continuation's sake, we have to do this. So these are the contents in ABC. This is the relation table. Let us relation to decompose the sub two relations where R1 has A and B attributes and R2 has B and C. So these are the leaf nodes or the child nodes. Child structure. For lossless decomposition, we have R union natural join operator with R2, which results in R. So this is R1 natural join operator with R2, which comes under the R relation. Now, if we perform the natural join of the sub relation R1, R2, we get like this. So whatever was the input, the same output we get. That is the relation is the original relation R. That is was written here. This relation is same as the original relation R. Thus, we conclude that above decomposition is lossless joint decomposition. dependency preserving. It is important constraint of the database. In the dependency preservative, at least one decomposed table must satisfy every dependency. In a relation R is decomposed into relation R1, R2, then the dependency of R either must be a part of R1 or R2 and must be derived from the combination of functional dependency R1, R2. For example, suppose there is a relation R has attributes A, B, C, D, and with functional dependency set A is depending on B, C, relation R is decomposed into R, A, B, C attributes and R2 with AD attribute, which is depending preserving because functional dependency A is depending on BC is a part of relation R1 with the attributes ABC. Let us understand this for the example. Employee project detail is the table name of this table or relation where the attributes are employee code, name, employee email, project name, and project ID. In this relation, we have the following functional dependency. Employee code is dependent on employee name, employee email. Project ID is dependent on project name. This two is one relation, this three is one relation. Okay. Next, after decomposing the relation into employee, project, and project detail, this is shown what I have told before. Employee is employee. A project has employee code, project ID, employee name, and employee email. In this relation, we have the following functional dependency where employee code is depend on employee name and employee email. In this relation, we have the following functional dependency where project ID is dependent on project name. Here, employee code is dependent on employee employee email. Next, we can see that all functional dependency in employee project detail is either part of employee project or employee project detail so that the decomposition is dependency preserving. Lossy joint decomposition. Consider there is a relation R which is decomposed into sub-relation R1, R2, and Rn till Rn. This decomposition is called lossy joint decomposition when the join of the sub-relation does not result in the same relation R that was decomposed. The natural join of sub-relation is always found to have some extraneous tuples. For lossy joint decomposition, we have the R1, the join of R2, join of natural join of R3, and natural join of R1. That is, all is nothing but a subset of or reverse set of R, which is a natural join operator. So consider the following relation. R is has attribute ABC. Consider the relation to decomposed into two relations of R1 and R2, where R1 has attributes A and C and R2 has attributes B and C. The two sub-relations are RABC divided into R1 of AC, R1 of BC, as shown in this structure. Now, the decomposition is lossy For lossy decomposition, we have our natural join of R2 is equal to R. Now we have performed the natural join of the sub-relation R1, R2. We get this problems related to decomposition. If the relation has no proper decomposition, then it may lead to problems of loss of information. Decomposition is used to eliminate some of the problems of bad design like anomalies, inconsistency, and redundancy. Unless we are careful, decomposing a relation schema can create more problems than it solves. Two more questions must be asked. Do we need to decompose relation? Is it necessary to decompose relation? What problems does the given decomposition cause? To help this with the first question, several normal forms have been proposed for relations. If the relational schema is one of these normal forms, certain kind of problems cannot arise. The normal form of a given relation schema can help us decide whether or not to decompose into further. So, so that gives the basis of normalization. If we decide that the natural relation schema must be decomposed further, we must choose a particular decomposition, that is, a particular collection of smaller relations to replace a given relation. With respect to the second question, two properties of decomposition are of particular interest. The lossless join property enable us to recover any instance of the decomposed relation for corresponding instances of the smaller relation. The dependency reservation property enable us to enforce any constraint on the original relation by simply enforcing some constraints on each of the smaller relation. A serious drawback of decomposition is that query over the original relation may require us to join the decomposed relation. In such queries are common, the performance penalty of decomposing the relation may not be acceptable. In this case, we may choose to live with some of the problems of redundancy and not decompose the relation. It is important to be aware of the potential problems caused by such residual redundancy in the design and to take steps to avoid them. Example, by adding some checks in application code. So next, coming to functional dependency. Functional dependency is a relation that exists with one attribute uniquely determines another attribute. Functional dependency is a form of integrity constant that can identify schema with redundant storage problem and to suggest refinement. A functional dependency a depends on B in a relation holds true if two tuples have the same value of attribute A, also have the same value of attribute B. If T1 dot X is equal to T2 dot X, then T1y is equal to T2y, where T1 and T2 are tuples and XY are attributes. Reasons about functional dependency, which is called Armstrong axioms, as we have revised in the previous videos. Armstrong axioms defines the set of rules for reasoning about functional dependency and also to infer all the functional dependency on the relational database. Various axiom rules and inference rules are primary axioms and secondary or derived axioms. Your rule number one is reflexivity, and number two is argumentation. Number three is transitivity. Okay. Now, reflexivity. What is reflexivity? Let us go through that. If A is a set of attributes and B is a subset of A, then A holds B. That is, A is nothing, is not holding as holding B. Argumentation. If A holds B and C is a set of attributes, then AC holds BC, where AC is depending on BC. It means that attribute independency that does not change the basic dependency. The third one is transitivity. If A holds B and B holds C and A holds C, so this is called transitivity, that A is depending on B and B is depending on C, then A is depending on C. That is, A is holding B and B is holding C and A is holding C. That A holding B and C is a set of attributes, then AC holds BC. That is AC holding BC. Give rise to aroma means hold. At this instant, secondary or derived axioms. Rule 1 is nothing but union. Rule 2 is nothing but decomposition. Rule 3 is nothing but pseudo-transitivity. Let's see what is rule 1. That is the union. If A holds B and A holds C, then A holds BC. If A is holding B and A is holding C, then A is holding BC. Next rule, decomposition. If A is holding BC and A is holds B, then A is also holding C. If A is holding BC, A is holding only B and then A is also holding C. Pseudo transitivity of rule 3 of secondary and derived axioms. If A is holding B and BC holding D and AC holds D, that is, A is holding B and BC is holding D, then AC is also holding D. Attribute closure. Attribute closure of the attribute set can be defined as set of attributes which can be functionally determined from it. Note, to find attribute closure of attribute set, add elements of attribute set to the result set. Recursively, add elements to the result set which can be functionally determined from the elements of result set. Types of functional dependency. The types are trivial function dependency, non-trivial functional dependency, prime and non-prime attributes. Trivial function dependency. If A is dependent on Y, is a functional dependency and Y is a subset of X. These type of functional dependency called as trivial functional dependency. Next, non-trivial functional dependency. If A is depending on Y and Y is not a subset of X, then it is called non-trivial functional dependency. Completely Non-trivial functional dependency, if A is depending on Y and X is intersection of Y is equal to empty set, that is null, then it is called completely non-trivial functional dependency. Prime and non-prime attributes. Attributes which are part of any candidate key of relation are called as prime attribute. Others are non-prime attributes. Candidate key. Candidate key is the minimum set of attributes of a relation which can use to identify a tuple uniquely. Consider student table where student is having attributes of SNO, S name, S phone and age. SNO means what? Student number. S name is student name. S phone is S phone number, student phone number and the age. We can take S number, that is SNO, as candidate key. We can have more than one candidate key in the table. Type of candidate keys can be simple and composite. Simple can having only one attribute, composite having multiple attributes as called candidate key. Super key is a set of attributes of a relation which is used to identify the tuple uniquely. Adding zero or more attributes to candidate key generally is called super key. A candidate key is a super key and vice versa is not true. Consider student table. The student have S number, S name, S phone and age. We can take S number as one and S number and S name as one set, that is in the bracket as super key. So next attribute closure. Attribute closure of the attribute set can be defined as set of attributes which are functionally determined for it. Note, to find attribute closure of the attribute set, add elements of attribute set to the result set. Recursively, add elements to the result set which is functionally determined for the elements of result set. Types of functional dependency we have seen here. So let's again go through it. Types is trivial functional dependency, non-trivial functional dependency, completely non-trivial dependency. And other is prime and not prime attributes are there. Attributes which is a part of any candidate key of relation is called prime attribute. Others are non-prime attributes. Candidate key, we have seen what is candidate key and what is super key. The next coming to normalization, we have already expressed what is normal forms, why we have to go for normal forms, what are the different anomalies, how we are facing with the redundancy, and how we are facing problems with the consistency, what are the different anomalies are there, and why we are approaching normalization. So again, the normalization, we are going to have a brief knowledge about this. Normalization is a process of designing a consistent data base with minimum redundancy, which supports data integrity by grading or decomposing given relation into smaller relation, preserving constraints on the relation. Normalization removes data redundancy and with the help in designing a good database which involves a set of normal forms. The sum of the normal forms is being addressed below. First normal form, second normal form, third normal form. We have gone through these normal forms in our laboratories. Next, Boyne's code normal form and the fourth normal form, fifth normal form, sixth normal form, and domain key normal form. But our syllabus is only 10 Boyne's first, second, third, that is BCNF, fourth and five, sixth and sixth and domain. I'll give you a future idea. I'll give you a small brief idea in the future classes. Normal forms are so many. So first normal form, what is going on? No repetitive data groups are going on. Second normal form, no partial key dependencies taking care. Third normal form, no transitive dependency is taking care. Boyle's code normal form reduces key dependency. Fourth normal form, no multiple value dependency. Fifth normal form, no joint dependency. I have to tell you one thing. The first normal form is no repetitive data group. Coming to the second normal form, the characteristics of first normal form and no partial key dependency. So first normal form is nothing but is also a set of is also a set of second normal form. This normal form is also a set of third normal form, and third normal. All these features of 1, 2, and 3 is also a set of BCNF, the characteristics and these properties of BCNF will be shown in fourth and the similar way on 5. So what is second normal form? The properties and the conditions of first normal form plus no partial key dependency. This is all going on so on. The properties are eliminates redundancy due to functional dependency. The third normal form is mostly it is done. BCNF is completely done, and fourth NF is also completely removed. Eliminates redundancy due to MVDs is no, and fourth normal form it is there. So the next is preserves functional dependency. Yes, maybe and maybe. Previous preserves MVD is maybe or maybe. So the tomorrow class we can see what is first normal form. So before that, let me give the brief introduction. So what is first normal form? As we have seen in the laboratories also. So first normal form, a relation is said to be first normal form if it contains all atomic values of the single value. The first normal form expects you to follow very simple rules while designing your database, and they are rule 1, single valued attribute domain should not change. So these are the examples for some of the examples, and rule 3 is unique names for attributes and columns, and rule 4 is order doesn't matter. So these are the examples we can go through in the next class. That is, we have to start our first normal form.